Hello guys, in this video we are going to see the relation between corresponding points in some special cases. We have seen this equation over here. This is the equation for a fundamental matrix. So we have come across this equation. Now what we are going to do in this video is given two images. So we have this image and this image, and we have some corresponding points, that is points in this image corresponding to uh, points in this image. So we just have to find out the relations between these 2 points in the two images in this video. So that will be the goal of this video. In some special cases, so we are going to see what are these special cases. So let's start. So we have seen this equation over here. This is the equation of fundamental matrix. So now just doing some basic things. So over here substituting p plus like this. So we know that p plus is nothing but the pseudo inverse or the least square estimate of p, where p is the projection matrix for this camera. So its equation is given like this. So just putting the value of p plus over here. Next, we know that if we do a setup like this, where the origin of the 3D world, this is our 3D world. So the origin of the 3D world is at this camera center. So in that case, the projective matrix for this camera will simply be this, where K is the intrinsic matrix of this camera. I is because there is no rotation, both are actually aligned. The world coordinates and the camera coordinates are aligned now. So because of that, there is a I over here, and 0 because there is no translation. Similarly, this camera with respect to this coordinates will be now written like this. So the k dash is the intrinsic matrix of this camera. There is r, so there may be some rotation, so that can be taken care by this r, and there is t, that is the translation, that this displacement over here, the translation t. So putting these values over here, so p dash is this thing, putting that over here, putting p that is over here, like this, you get this equation. It is quite straightforward, just substituting the values. Now you will see that over here, if you see this thing over here, so this I gets multiplied with r, and this 0 gets multiplied with t. So because of that, that t goes out, and you are just left with k dash r and k transpose. So this k transpose is over here. Next, if you see this thing over here, this is I into I and 0 into 0. So I into I will give you I, and 0 into 0 will give you nothing. So you get I over here, which can also be just taken out. And then you have k transpose, so that is this thing over here, and you have its inverse. So if you put the inverse inside, you will have to change the positions. So you get k inverse transpose k inverse, and if you see there is a k transpose sitting over here, so these both get cancelled, and you are left with this thing over here. Now if you see this e dash, so this e dash is nothing but the epipole over here. This epipole is our e dash. So what is e dash? E dash is nothing but the projection of the camera center, this camera center, onto this camera. So if I just project this point on this image plane, I get my epipole. So this thing can be written like this. I am projecting C, so this is C, I am projecting C onto this camera, that is given by P dash. So I can write epipole E dash as P dash C. I hope this is clear. It's quite straightforward. I'm just projecting this point on this image, and that is my epipole. So I have P dash C over here, and C, if you see, C is nothing but this vector, because C is the origin of the coordinate system. So it will be given by 0, 0, 0 and 1. So this 1 is because of the homogeneous coordinate system. So if you put that over here, so we know P dash is this thing over here, K dash RT, and you see that there is this C over here, which has 3 upper coordinates as 0. So what will happen is when you multiply this P dash with C, this 0, 0, 0 will basically make this r 0, so there will be no r, and this 1 will preserve the t. So there will be, you'll only be left with k dash, which is over here, k dash and t, because this 1 is preserving the t and it is removing r. So this is the equation that we get for a fundamental matrix in terms of the intrinsic parameters and this r. So in this case, so here we had an equation which was in terms of P, that is this projective matrix. Now it is in terms of these intrinsic parameters and this R and T, that is the intrinsic and extrinsic parameters of the camera matrix. So we have found this pretty looking equation over here. Okay, with that, now let us go to our special cases. So one special case is pure translation. So this is also the case that we have seen in stereo, but this is a more generalized thing. Here you can move anywhere. So there we saw that it was just restrained in X direction, but over here this is pure translation. You can move upwards, you can move behind, or anywhere you can move. Just the constraint, you cannot rotate. So there is no rotation of these camera matrices or cameras. There is just translation, pure translation of the camera. Let us see what relation between the coordinates over here and the corresponding coordinates over here will be for this particular case. Let us see that. So we have derived this equation in our previous slide. Now just putting that special things. So for a special case, P over here, this P, say P is for this matrix, say this camera. So the P over here will be KI0. So I assume that the camera center over here is the origin of the world coordinate, and because that is the origin, so I can denote it like this, KI0. And similarly this camera will be denoted as KIT. Why? Because there is no rotation. I know because there is no rotation because I have taken a special case. So no rotation, only pure translation T. So this camera is just translated by this other camera, and there is no rotation or anything else, and there is some K. Also note that, say assuming the intrinsic camera matrix of both the cameras is the same, so both have common intrinsic camera matrix, that is K. This can be a case when the photograph is taken from actually the same camera. You place the camera over here, click the photo, then translate the camera, place it over here and click the photo. That can be one case. So like this, we can now modify this equation according to these things over here. So we see that K dash is just K over here, so we get this. So this R becomes I over here, so hence there is no R over here because that has become I, which can just go away. And we have K dash K inverse, that is over here. So now this is K dash, which is also what we are taking as K. So this is K inverse, so this will just go out. And over here we'll have KT, so this is KT, that's it. Now you can see that this is one of the form of K. So you have the focal length, you have skew parameter, and this XY thing over here. And there is T, the translational vector. So this will tell you how much translation in X direction, how much translation in Y direction, how much translation in Z direction. So that is this T. So if you see, if you just multiply these two things, so that is just multiply these two things, you will get this thing over here. And that is FTX plus STY plus PXTZ. So that is the first thing. Like this, you will get this particular thing. And please note that this is the cross product notation. So this is actually a matrix, but it can be represented by this vector. So this is a skew symmetric matrix. We have seen that in our previous videos. Okay, so moving forward, now say going into more special case, just for an intuition to this. So we just say translation in X, only translation in X. So this is exactly similar to the stereo disparity case that we discussed in our previous video. It is exactly translation only in X direction, no translation in Y, no translation in Z. So in that case, what will happen is ty tz will become 0 because there is only translation in x. So this vector over here will now become like this. This thing will become this thing over here because ty and tz is 0 because I'm constraining now that we only need translation in x. That's it. So this is what is going to happen. And if you see carefully, this thing over here is nothing but actually the epipole. If you just compare it, if you see this thing that we have is uh, is this thing over here. So this thing came from this kt. We saw that this kt, and this kt actually came from here, this thing, and that is nothing but our epipole actually. So we brought up kt because of this epipole. So this epipole is what we have got now. So this thing, this ftx 00 is nothing but actually the epipole e dash, and not exactly the epipole, but it is the cross product matrix of the epipole. So one more thing that one can note, that you can see that this is the epipole. So this is a point. So here if I show you this thing over here, so it is a point over here. This point is epipole. So a point can be denoted by x, y, and the homogeneous coordinate w. So this is the x coordinate of epipole, this is the y coordinate, and this is that homogeneous coordinate over here. So if you see, this homogeneous coordinate is actually 0. So we know that when the homogeneous coordinate is 0, this point is actually at infinity. So only when this point will be at infinity, only at that point of time, this thing will be 0. The homogeneous coordinate will be 0. So that can be verified quite easily. We know that all the lines, the epipolar lines over here, are actually parallel to each other, and they are not only parallel, but they are also this horizontal lines that we have. So that is our stereo disparity case. So over here you can mathematically see that this thing, the epipole over here, is actually at infinity. So these parallel lines will actually just meet at infinity. So one important thing about this ideal point, or the point at infinity, is that you can just scale that point as in you want, because since this point is at infinity, you just need its direction. That is enough to represent the point. So even if this is ftx, or if it is 2, if it is 3, that doesn't matter. You can put any number over here as long as the direction is the same. So the one can say the unit vector of this thing is this thing. So why this thing is true can be covered in some other video discussing about ideal points at infinity. But for now, we can just say that for points that are lying on infinity, it is only the direction which is important. These magnitudes are not important. It is just the direction which will tell me a point at infinity. So over here, since this is a scalar value, f is the focal point, tx is a number, the translation in x. So this is a scalar value, and this whole thing is a vector. So we are just taking its unit vector, or just taking its direction, and that can also be represented as the epipole. And now if you just make this thing like this, that is just remove the cross product notation and bring in the actual matrix, you will get the fundamental matrix, that is in this case for translation only in x. So the fundamental matrix, if you want to see for this stereo disparity case where the translation was constricted to x, so this is that matrix. So you can just recall how we got this matrix. Here, if there is a vector like this, then the cross product notation is given by this matrix over here. So you can see that E1 comes over here, and we had E2 and E3 0. So it is only this thing and this thing that is going to be there, and all other things will just be 0. Right, so this is the fundamental matrix corresponding to the stereo disparity case. Now, this we have seen this stereo disparity case fundamental matrix. Now we know that this is our epipolar constraint. So if we just put this fundamental matrix in this epipolar constraint equation and you work out, so it is very simple. This is the x, y and 1. So that is points corresponding over here. So this x are points corresponding over here and x dash are points corresponding over here, and you just multiply these. So you will see that x, there is nothing over here because all are 0. You will see a -1 over here, and you will see a y over here. And similarly, when you multiply these two, you will get this equation minus y dash plus y is equal to 0. So that finally gives you y is equal to y dash. So over here, this was quite intuitive. So I'm just mathematically deriving the cases that we saw in our stereo disparity video. So we know that for a stereo disparity case, a point y over here will be equal to a point y over here. So the y coordinate of this point, the y coordinate of this point over here will be equal to the y coordinate of the corresponding point in this image. So that is the stereo disparity case. So to first of all tell you how does the fundamental matrix of a stereo disparity case looks like. So this is what it looks like, and we get the case over here. So I'm just deriving mathematically the equations that we got in our stereo disparity case. Okay, so now let us also see the disparity equation. So we have derived the disparity equation for the stereo disparity case where we had restricted the translation in x direction. Now we are going to derive a general disparity equation for any translational motion. So now say this camera is purely translating anywhere in the 3D world, not only restricted to x direction, then what will the disparity equation for such a scenario look like? So that is what we are going to derive. So x over here, so say, okay, so this is p now. So this is our p camera matrix and this is our p dash. So points over here will be x. This x will denote points over here, and x dash, which we'll see in the next slide, will denote points over here. Okay, so we have x is equal to px. So all the points over here will be just the image of this object that is over here. So this object or the coordinates, the 3D world coordinates are denoted by capital X, and the small 2D coordinates over here are denoted by x. So this object, say we are taking the image of this object, so this object is coming over here, and hence we can say that capital X is equal to px. Sorry, small x is equal to px, where p is the projective matrix for this camera. Okay, now since we are assuming that our this coordinates, the 3D world coordinates is in this camera, is merged with this camera, so hence we can get this equation which we are just looking from all the previous slides. So p is this thing over here, and just substituting that over here, we get this. Now if you just multiply this this thing with this x, you'll get x cap, where x cap is the inhomogeneous coordinates of x. So that is just to right. So just revisiting this thing. So we have our intrinsic camera matrix over here, we have extrinsic camera matrix, and this is our 3D world homogeneous coordinates. So if you see over here, this thing is 0 and this thing is identity. So what will happen is these three things will remain because there is this identity over here. So x will remain, y will remain, and z will remain if this becomes identity. And since all these things are 0, so this 1 will go off. So we are going to get, after multiplication of these two things, we are going to get only this x, y and z. So that is what I call as my inhomogeneous coordinates for the 3D world. So since there is a I over here and a 0 over here, so the 1 that is there over here in this 4-dimensional matrix, the 1 will just go out and you will only be left with x, y, z over here. So this is what I've written simply because this special equation is what we have. Okay, so now x cap is this, and also if you see x, small x, so it can be denoted like this, x, y and w. So x coordinate, y coordinate and the homogeneous w. Okay, now just doing a small change. Okay, first taking this over here, so taking the inverse because we want a relation, this kind of a relation. Why, that will be clear in the next slide. So getting this k, so getting this k over here, so that will become k inverse since k is the intrinsic matrix. And just doing a small thing over here, so I am doing w by w over here. That will not make a difference. And next what we are doing is we are dividing by w. We are taking this w inside the matrix. So what will happen is there will be a x by w, y by w, and there is will be a 1 over here. Please note that this 1 is not bold. This is a mistake. So this should be a small scalar 1. This is a scalar value, right? Okay, so this is what we have, and I just took this w outside because that is again a scalar. So these all non-bold letters are scalars. Okay, and by this equation we can very nicely get that w is equal to z. So we have also seen this in our stereo case or in a video after camera matrix that w is nothing but z. So we can replace this w by z, where z is our 3D world coordinate, this z over here, and this thing x by w, y by w1, these are nothing but the coordinates on this image. So these things are precisely the coordinates on this image, and this k inverse is our intrinsic matrix, and there is this z over here. So we get this quite nice result that x cap, that is the inhomogeneous coordinates x, y and z, are nothing but z k inverse x. So this result will be used in the next slide. Now going on to the other camera. So for x dash, so for this camera the equation will be x dash is equal to p dash x. Just putting p dash value over here, so p dash will now be it because it is translated, so t, no rotation, hence I. So this is the equation for that. And next just doing the same thing over here. So over here you will see that because there is this t, and in the previous case this was 0, hence the 1 over here, the 1 in this just went off, but because there is this t over here, so this will preserve this 1, and hence now we can write x as say x cap with a 1. So these are the inhomogeneous coordinates x, y and z with a 1 over here, and just multiplying it again. So what we see is we get a k ix, which is just kx cap, sorry, x cap, and plus we get a kt into 1, so that is kt. So this is the equation that we get. Now doing some changes. So this x cap we saw in the previous slide, this. So this is the x cap is equal to z k inverse x. So just putting this z k inverse x over here in this place. So just putting that over here, we get this thing over here, z k inverse x. So just I took z out because that is a scalar value over here, and this kt is as the same. Now we have x dash is equal to this thing, if you see, just goes off because this is inverse, so this will cut off and you will get zx plus you have this kt over here. Okay, now the same thing for x dash. So you can just repeat the same process. You can multiply a w, divide by a w. So over here there will be a w dash, and there will be a w which will remain over here, and you can put the upon w inside. So these are the coordinates of this image. So these are precisely the coordinates on this image, and this w dash can again be written as z. So we have z x dash, so this whole vector is x dash, plus zx plus kt, and just dividing by z on both the sides, you get this equation. So this is the general disparity equation for pure translation. If you now translate anywhere in the 3D world, but it should be pure translation, no rotation of cameras, then you can relate the points that are corresponding over here. So say in this video, in this case, this point over here corresponds to this point, and similarly this point over here corresponds to this point. So these corresponding points can be related by this equation, this simple looking equation over here. So now over here, if you just take a special case of this only translation in x, then you will see that this kt just becomes fx. So here you have seen that I have multiplied here. If you see that this kt over here, where I am multiplying both of these things, so this kt becomes this vector, and when you make translation only in x, so what will happen is this ty and tz will become 0, so these all things will become 0, and you'll get this vector over here. So you just have ftx. So that is the stereo disparity equation actually. So here you will have ftx, and this equation then becomes the stereo disparity equation, that is only translation in x. So this is a general equation for any kind of translation that you can think of. So this is the general disparity equation that we have got. Okay, now let us see the pure rotation case. So earlier we saw a pure translation case. Now we are going to see a pure rotation case where this red camera this red plane can be thought of as a one camera, and this blue can be thought of as a other camera. So here the camera center for both the cameras is the same. The only difference is that the cameras are rotated, that's it. So if you see the camera matrices for these two cameras, there will be something like this. So one is ki0 and the other is k-r0. So there is no translation in any of the matrix, that is no translation in any of the cameras, and just the rotation that can be given by this r, that's it. So if you see the two images that can be acquired of this object by these two camera position, so there will be something like this. It is just purely rotated, that's it. There is no other change. Okay, let us see the equation, the disparity equation for a case like this. So if you see, okay, you cannot call this as a disparity equation. So just a relation between the two coordinates, that is x and x dash, corresponding points, the relation between the corresponding points. Let us see that. So we have x is equal to px. So for this blue square, let us consider that as having camera matrix as p, and the red is having camera matrix p dash. So x are points on the blue image plane. So x is equal to px, just putting this p again, and this becomes like this. So again there is a 0 over here, so that will remove that 1 that is sitting inside this, the homogeneous one, and that will just give you this inhomogeneous coordinates x cap. So this is what we have, and just going through the same lines of derivation that we saw over here, we'll see that x dash x cap is again z k inverse x. So same thing can be repeated over here, and we get this thing over here. Now for x dash there will be a small change. So now because x dash is also r0, so again this thing, this 0 will again cut out the 1, so again there will be an x cap over here. Okay, and there is this r and k dash. So this is our equation now. So it is quite similar to this thing, just the difference is that instead of I there is r, that's it. Okay, and now just replacing this x cap over here with this equation over here, so we get z k dash r, and instead of x cap we have z k inverse x. So because this z is a scalar, so you can just move it around anywhere you want. And with the similar equations over here, so we can just convert this x dash to zx dash actually, where this x dash is actual coordinates that we have on the image, right? So just converting that, again cancelling this z that we have, so we get this equation. So the relation between points over here, corresponding points over here to those corresponding points over here, can be given like this. So an example, this point corresponds to this point corresponds to this point, and so on. So one can see over here that there is no capital X. That is, if you see in the previous case, there was this Z. So this Z was one of the element of this capital X, the 3D world Z. But if you see this equation, there is no 3D world point, no x, y, z, nothing. So this, and if you see this matrix over here, so this is a 3 cross 3 matrix, the intrinsic matrix. This is a 3 cross 3 rotation matrix, and this is again a 3 cross 3 matrix. So if you just multiply all these, you'll get some 3 cross 3 matrix, which can be referred as a homography matrix. So when you have just pure rotation, your transformation between, or what you can say, the relation between the two corresponding points is nothing but a pure homography transform. It is not like a disparity case over here, where you have some disparity, that is, you have some differences. There will be some different motion for the things that are ahead and different motion for the things that are behind. There is not such case in pure rotation. So pure rotation can be just given by a simple 2D homography matrix. So that is what we see, that is the main thing of this video. So we saw two special cases, pure rotation and pure translation, and we saw, or we derived the equations between x dash and x, which are the corresponding points of the two images, and the relation between them. We derived the relation between them. So that's the main purpose of this video. Thank you so much for watching. Thank you.